Welcome to example number 5. This example involves a velocity selector, which is essentially a device that separates the different charged ions that would be coming into a mass spectrometer to make sure that they all have the same speed, regardless of the mass or charge that they have. So what will happen in this problem is we'll see two fields being crossed, an electric field and a magnetic field, such that this beam of charged particles as it moves through between these two plates is going to continue in a straight line. It's going to be able to continue in a straight line because the two forces are going to cancel each other out. Here's an animation of a charged particle entering a uniform electric field pointing upwards. So this charged particle, you can see that is being accelerated in this vertical direction and causing it to deviate in path. We want to have that charged particle move in a straight line. So we need to introduce a magnetic field into the situation so that we can balance out these forces. So let me reset here and we'll relaunch this and see if we can play around with this magnetic field. If I make it too weak, you can see the electric force is stronger upwards, and so it's going to continue upwards. If I make it too strong coming out of the page, then the force is stronger going downwards from this magnetic force, and so the path deviates this way. So let's try to adjust it just right so that it will go right in a nice straight line. And so there must be some strength, or the ratio of these strengths, of the electric field going upwards and the magnetic field coming out of the page, which is going to cause a straight line. Let's take a look at the mathematics now. So if we were going to draw the free body diagram for this charged particle as it is inside the between the two plates here, we would see that there would be two forces acting on it. Now you can see that this battery is arranged so that this is the positive terminal over here, which means that this plate down here is all positively charged. And then the top plate is equally negatively charged on the other side. So we have a negative Q and a positive Q here. And that means we have an electric field that is pointing directly upwards. So there's our electric field pointing upwards, which means when that charged particle is in that field, it will have a force exerting upwards here called the electric force. And if you recall, the electric force is equal to Q times E, the strength of that field. And at the same time, we'll need an equal and opposite force acting straight down called the magnetic force, FB, which is equal to Q times V times B times sine theta. But sine theta will be 1 because our field is going to be arranged so that it's perpendicular to the velocity. So we have the velocity going along this plane of the screen here, the field going straight up, and now we need to determine what direction that electric or magnetic field is going to point. Using your right hand rule, so if you have to drop the pencil and pull your right hand out, point your thumb to the right of the screen. Make sure your palm is facing downwards to the bottom of the screen, and then see what direction your fingers would point in order for this to occur. So with the thumb going to the right and the palm of your hand facing downwards, you'll see that your fingers will be pointing out towards you, out of the screen. It means we have a magnetic field that is pointing outwards, away from the screen. So what I've drawn is a bunch of red dots to represent the magnetic field that is out of the plane of the screen. So now, solving part A, we note that the sum of the forces should balance out to be 0. It means the electric force upwards minus the magnetic force downwards will be equal to 0, or the magnitude of both of those forces will be equal to each other. Now the magnitude of the electric force is equal to Q times E, and the magnitude of the magnetic force is Q times V, the velocity of this charged particle, which is V here, times the strength of the field B. And you can see that the charge Q cancels out. And so then the velocity of this charged particle is equal to the ratio of the electric field to the magnetic field. Well, we're looking for the magnetic field, B, so let's just rearrange this equation and write E divided by the velocity. But they don't give you the strength of the electric field. What they give you is the voltage and the distance between the two plates. So you have to recall an important formula you learned earlier, that the electric field is related somehow to the voltage and the displacement between the two plates. Hopefully you recall that the voltage, delta V, or sometimes just written as V, is equal to negative E times D. It's very typical at this point to erase the delta V and just think it as V, which is the voltage. And also we drop the negative because really the negative is only there because as you go in the direction of the electric field, your potential drops. And we don't care about that. We're looking for magnitudes. So therefore, the electric field strength is equal to the voltage divided by the distance between the two plates. So let's substitute that into the equation. We get B equals V divided by D divided by the velocity. Or I suppose you could write it as the voltage divided by the distance times the velocity. So let's now substitute in. We have a voltage between the two plates of 150 volts. And then we have the distance between the two plates as 4.5 centimeters. So that's 0.045 meters. And then we have the velocity of this particle, which is 3.25 kilometers per second. So that's 3.25 times 1,000 because we need to change kilometers to meters per second. And this gives you an answer of 1.02 Teslas. And for part B, we've sort of answered it already. Because this plate is positively charged down here and this is negatively charged, we have an electric field that is pointing straight upwards, which causes an electric force on, say, a positively charged particle upwards. So to compensate for this and create a magnetic force going downwards to balance these two forces, we have a magnetic force going downwards. And then using your right hand rule with the velocity to the right, your thumb to the right, your palm facing down, the magnetic field lines must point perpendicularly out of the page or screen that you're looking at. And there's my answer written down here. And that's it for example 5.